Hello everybody, my name is David and I am an engineer at Arup. In this presentation I will explain how we used a series of LS-DYNA implicit tools to predict the fatigue performance of an adhesively bonded electric vehicle battery enclosure across a range of imposed loading inputs. Before getting into this specific topic, I should zoom out to display the full range of automotive capabilities that we have at Arup using LS-DYNA and the Oasys software suite. These capabilities include dozens of vehicle crash load cases, pedestrian and occupant safety load cases, NVH, structural durability, and load cases on the vehicle closures. We have delivered these capabilities to a wide range of automotive OEMs on consulting projects over the past few decades. With the rise of electric vehicles in recent years, a subset of our automotive capability now focuses on electric vehicle batteries and battery enclosures. LS-DYNA simulations are used for the design of these structures in order to align with legislations around EV battery enclosures. As well as designing for structural strength and stiffness, LS-DYNA has been used to perform a range of thermal and fluid dynamic analyses, but the focus of this presentation is on a range of analyses to assess the battery enclosure's structural fatigue performance. During this webinar, I will discuss the theoretical background to fatigue assessments, the need for fatigue assessments of EV battery enclosures, and then move on to our LS-DYNA implicit approach to achieving this assessment. I will explain the specific methodology required for predicting fatigue of adhesive bonds. The full fatigue assessment of the adhesive and the aluminium will be demonstrated by using an example LS-DYNA model and showcasing some typical analysis results. So, what is fatigue? The Eurocode 9 definition describes it as the weakening of a structural component through crack initiation and propagation caused by repeated stress fluctuations. If we look at this time history of a random stress signal, which could represent the stress in any region of a structural component due to external applied loading, then we can see lots of cycles at various frequencies and amplitudes, where the peak-to-peak is known as a stress range. These amplitudes may be significantly lower than the component's yield stress, but component failure due to fatigue can occur after a large enough number of small amplitude stress cycles. This stress time history can be assessed using a material-specific SN curve, where the S-axis represents each stress range present in the time history, and the N-axis represents the number of cycles of that particular stress range for failure to occur. In the region above this yield stress, material behavior is non-elastic and it should only take one cycle for failure to occur. In theory, some materials such as steel have an endurance limit, which is a stress range below which the structure should be able to withstand an infinite number of low stress cycles without failing. For aluminium, very low stresses do still have an effect, so there is typically not a hard endurance limit, as illustrated on the graph. In a random time history such as the one shown, there will be a very large number of stress ranges present, but we can pull out 3 stress ranges for illustrative purposes and map them onto the SN curve. It can be seen that the largest stress range will fail due to fatigue after the smallest number of cycles. The number of cycles at each stress range present within time history can be determined using methods such as rainflow cycle counting. Putting some arbitrary numbers to these 3 stress ranges and using something known as Miner's rule, we can calculate the cumulative damage ratio for that material based on the stress time history that it was subjected to. Let's say that we know that it was exposed to 20,000 cycles of the 100 megapascal stress range, with 100,000 cycles being theoretically required for failure, then this is a ratio of 0.2. By considering the other 2 stress ranges and then doing a summation, we can see that the cumulative damage ratio in this example is 0.7, or 70% of the way to failure, or at 70% fatigue life. It is important to consider the fatigue risks for EV battery enclosures due to the important job that they have to perform for a vehicle on the road. The battery enclosure must have sufficient strength and stiffness to protect the enclosed batteries in the event of a vehicle crash, to contribute to the overall stiffness of the vehicle, to provide containment of heat, pressure and fire in the event of a thermal runaway, and to withstand the inertial loads from the mass of the batteries. The total mass of the battery modules plus enclosure can typically be in the range of 0.5 to a ton, which can be around 25% of the total vehicle mass, so very significant. The connections on lightweight aluminium structures can be welded, bolted, or fixed with adhesive bonds. One issue with spot welding is that it is difficult to achieve without weakening the parent material in the weld region, the heat affected zone or HAZ. Other issues arise from thermomechanical effects such as crack formation during heating and cooling cycles of the weld region, affecting fatigue life. The aluminium material is not negatively affected in the same ways when connected via adhesive bonds. Stress concentrations occurring around lots of small spot welds would be expected to be more severe than those occurring around large, smeared areas of adhesive bond. Adhesive bonding of aluminium battery enclosures is the focus for the rest of this presentation. Taking a look at our example LS-DYNA model, it is geometrically typical for an EV battery enclosure located underneath the vehicle. The rest of the vehicle has not been modelled, so the mounting points for the battery enclosure have conservatively been given stiff 6 degree of freedom SPC restraints. The aluminium battery enclosure has been modelled using thin shells, as has each of the 10 battery modules. These components have been bolted together on the cross members using beam elements and nodal rigid bodies. The adhesive bonds occur on the joints which connect the cross members to the side members, which we can zoom into now. These connections use tied contacts between the adhesive solid elements and the aluminium shell mid-surfaces on either side. A material definition for matte Arup adhesive was used for the adhesive, which allowed for a stiffness correction to match a true 0.3 mm bond thickness, despite the solid element thickness being much greater than this. In the image on the right, we have the adhesive joint with the aluminium thin shells visualized with true thickness, revealing the 0.3 mm air gap, representing the true bond thickness, compared to the actual thickness of the adhesive solid elements. Now we will compare fatigue assessments using random vibration between the time domain approach and the frequency domain approach. Physical testing is naturally limited to the time domain, where a test specimen is given a random loading sequence until the specimen fails. With FE analysis, we can either apply a time domain input loading and receive time domain stress results for each element in the model, or apply a frequency domain input in the form of a PSD, power spectral density, and receive PSD stress results as output. Each approach requires a different method to determine the number of cycles at each stress range in the element results, but then the approach of calculating fatigue damage using the material SN curve and minors rule is the same for each approach. The time domain approach is a slower analysis and produces far more data, therefore it is necessary to focus on regions of greatest importance and only request results for a subset of elements. However, it is the most flexible approach due to the options available for post-processing time history results for assessing fatigue, such as rainflow cycle counting. The frequency domain approach is a much faster analysis and produces a lot less data, therefore results for all elements can be requested, and it is easier to do lots of design iterations and sensitivity studies, but we are constrained to a few standard frequency domain fatigue assessment methods. The specific input vibration loading used here has come from the GB 38031 2020 China Standard Regulations for electric vehicle vibration load cases. The sequence of tests comprises 12 hours of random vibration loading in the Z direction, defined by a PSD, followed by 1 hour of fixed sine wave loading at 24 Hz and 1.5 G amplitude in the Z direction, followed by equivalent durations of loading in the Y and X directions, as shown graphically here. To achieve this mixture of random vibration loading and fixed sine wave loading, the following implicit analysis keywords were needed. For both adhesive and aluminium, the fixed sine wave loading was achieved with a star frequency domain keyword variant. For random vibration, the aluminium was also analysed in the frequency domain using a different star frequency domain keyword variant, whereas the adhesive was analysed in the time domain using a definition on a variant of star control implicit. The reason for analysing the adhesive in the time domain was to enable the fatigue post-processing calculations to be performed by something known as the Sousa method, which required time histories of the adhesive element stresses. The Sousa method will be explained shortly. Due to the requirement of using both the time domain and frequency domain approaches, we needed equivalent time domain signals for the Z, Y, and X PSDs given in the China standard regulations. We created a MATLAB script which generated random time signals from each PSD. It was necessary for the time signal to be long enough to accurately capture the contents of the PSD. A good check for this was to create a new PSD from the generated time signal and compare to the original PSD. There should be negligible discrepancy. The first part of the implicit analysis sequence was to compute the structural modes using an eigenvalue approach. The first three modes are animated here. To estimate the number of cycles within the 12-hour load case, we made the lower bound assumption that vibration is purely at the frequency of the first mode, 42.7 Hz, hence leading to approximately 1.8 million cycles in this example. For the adhesive, computed in the time domain for random vibration loading, we adopt the previously mentioned Sousa method to determine the stress ranges. A paper by Sousa et al. Derives an effective stress, which can be computed at each moment in time by knowing the von Mises stress and hydrostatic stress in each element. This effective stress was shown by Sousa to correlate best to fatigue damage for adhesive bonds. With this newly calculated effective stress time history, we can either do rainflow cycle counting or, in this case, approximate by using the RMS value of effective stress. With this RMS value of effective stress, we map it onto a Gaussian distribution by saying that it represents the one standard deviation value of stress. Using the Steinberg three-band method, we use the 1 standard deviation, 2 standard deviation, and 3 standard deviation values of stress, which occur 68.3%, 27.1%, and 4.3% of the time respectively in that particular element. The 1, 2, and 3 standard deviation values are then mapped onto the SN curve for an adhesive. In this case, an adhesive with 23.1 MPa shear strength, also derived by Sousa. This gives us our equivalent N1, N2, and N3 values for number of cycles to failure, and we have already estimated our number of cycles in the load case from the fundamental frequency in the eigenvalue results. This then enables the fatigue damage ratio to be determined, where any damage value greater than 1 means a prediction of failure due to fatigue. It is a different approach for the aluminium, which is computed purely in the frequency domain, so the stress ranges are determined using the Dirichlet method embedded within LS-DYNA. This method converts the element PSD into a probability density function to create the stress ranges, and by knowing the exposure time of the PSD, 12 hours, it is enough to calculate cycles and hence the fatigue damage ratio. This time using an aluminium-specific SN curve, which are given in Eurocode 9. Before looking into a set of example results, it is important to understand that there will be sensitivity in the fatigue damage results due to some of the key inputs, such as the level of modal damping assumed, the number of modes chosen to be used in the modal superposition, the mesh resolution, and the element quality. Analysis verification with sensitivity studies is recommended. If fatigue damage is above or below targets, then local structural modifications can be made to increase or reduce the stiffness or mass. Perhaps resizing or redistributing the adhesive bond area, whilst remembering that performance needs to be achieved across the combination of all other load cases such as crash and NVH. So, now to look at some example results. First, looking at some element stresses from a Z direction PSD of random vibration. The aluminium peak von Mises stress anywhere on the battery enclosure from the D3RMS file is 24 megapascals, giving a 3 standard deviation value of 72 megapascals, significantly lower than the aluminium yield value of 360 megapascals. For the adhesive, the peak effective stress, post-processed using the Sousa method, is 7 megapascals, giving a 3 standard deviation value of 21 megapascals, which is lower than a typical adhesive bond shear failure value of 25 megapascals. By viewing individual element PSD outputs in THIS, it can be seen that a stress peak occurs at the first eigenmode of the structure, and given that this adhesive joint is participating in that first mode, this is a good check that the results make sense. The upper graph shows all components of stress for one solid element, and the lower graph shows von Mises stress plotted for a row of solid elements in this adhesive joint. They all have similar curve profiles with different peak magnitudes corresponding correctly with the contours obtained from the D3RMS file viewed in D3plot. Now we look at fatigue damage ratio contour plots from the analysis using a Z-direction PSD input of random vibration. The aluminium values come direct from the D3FTG file from the frequency domain analysis, whereas the adhesive values have come from our scripted post-processing using the Sousa and Steinberg methods from the time domain analysis. In this example, we can see that the aluminium is predicted to fail locally before the adhesive, due to the higher peak fatigue damage ratio values. Looking at one key adhesive element, the summation across all 6 load cases gives a fatigue damage value of 8.5, which clearly exceeds 1, the value at which failure due to fatigue is likely. In this case, we can see that the contribution is almost entirely from the X-direction PSD of random vibration, so clearly some design iterations should be considered to reduce the peak values in all elements to below a fatigue damage value of 1. Now looking at one key aluminium element, the summation across all 6 load cases gives a fatigue damage value of 0.7, noting that almost the entire contribution comes from the 3 random vibration load cases. Given that the China standard regulations are supposed to mimic an accelerated version of reality, the fact that the aluminium has remained below a value of 1 for fatigue damage summed across all load cases is a very good sign that fatigue failure in the aluminium is unlikely during the operational life of this battery enclosure design. Zooming out to view an overall summary of this methodology, this table shows the inputs, the most important LS-DYNA implicit keyword, and the outputs required to obtain fatigue damage results for every adhesive element and every aluminium element of interest in the LS-DYNA model of the battery enclosure. We have a mixture of random vibration and fixed sine wave loading as input to achieve this China standard regulations, and we make use of the time domain approach with Sousa's effective stress for the adhesive solids, otherwise using a frequency domain approach. Now I will highlight the key benefits of using this LS-DYNA implicit methodology for fatigue assessment of structures. Specifically when assessing adhesive, the time domain approach allows for Sousa's method of predicting damage via effective stress to be used. In general, this methodology allows for the same LS-DYNA model to be used for implicit load cases, fatigue NVH, as for the explicit load cases, crash pedestrian, eliminating the need to convert the explicit LS-DYNA model to use with other FEA packages. This enables a more streamlined CAE workflow, which is quicker and cheaper to assess design iterations, as well as being easier to do quality assessment on the model, given that engineers only need familiarity with LS-DYNA, not multiple FEA packages. It is important also to note that this LS-DYNA methodology is not limited to adhesively bonded structures, but also to structures containing welded and bolted connections. Turning again to the Arup and Oasys capabilities around electric vehicle battery consulting, we can see where fatigue analysis fits into the bigger picture of design. Some of the specific Oasys software tools used during this LS-DYNA fatigue assessment methodology include the Primer Implicit Analysis Setup tool, the Primer Connections Manager tool, and a range of other powerful everyday primer tools whilst creating and modifying the LS-DYNA model. D3plot is fully compatible with the D3RMS, D3FTG, and D3SSD files which get generated by LS-DYNA from these analyses. And THIS is powerful for reading and comparing frequency domain PSD results, as well as the time domain data. And Reporter was useful in allowing the creation of bespoke templates to view summaries of the stress and fatigue results, both graphically and with contours, across the range of time domain and frequency domain analyses which were computed. Thank you very much for listening to this presentation. If you have any questions, then please feel free to email our team at dyna.support@arup.com or visit our website to find out more about our electric vehicle consulting services. Beyond the topic of this webinar, the Oasys team at Arup offer a wide range of webinars and training courses. Attendance of these training courses is complimentary to all of our clients, and you can register your interest via the web address shown on screen. Our website also contains a full list of past webinars available to watch on demand at any time. We also have an Oasys LS-DYNA newsletter, which you can sign up to receive news and updates monthly via email relating to our software releases, our training, webinars, and external events. And please consider following the Oasys LS-DYNA environment on our social media platforms of LinkedIn and YouTube, where content is posted on a regular basis. Thanks again.